We have been discussing the derivation of continuity equation. Now we derived the general equation of continuity equation. Now we shall consider a few special cases and how the equation is modified under those circumstances or under those assumptions. Some of them are, for example, when we derived the general equation, we assumed that the motion is time dependent and the fluid flow, the fluid is compressible. But in special circumstances, it can be incompressible fluid, it can be a steady motion, and so it could be a circular motion. So all these are different phases, different aspects of the equation, and that is what we will be looking at. So first we look at steady compressible flow. Steady compressible flow means that the flow is not time dependent, so time will have no effect on that, and therefore the derivative that was occurring due to time has disappeared, and now the equation is only reduced to divergence of rho v equals 0. So the aspect of compressibility is here because if density changes, if the fluid is compressible, the density will change, and therefore we have divergence of rho into the vector v. V represents the velocity is equal to 0, and this is the vector form. If we write it in Cartesian coordinates or the rectangular coordinates, then this will be transformed to delta by delta x of rho of u, delta by delta y of rho of v, delta by delta z of rho of w, where u, v, w are velocity components in x, y, z direction of the respective coordinates that we normally consider. If we were to consider the cylindrical coordinates that are normally taken to be r, theta, z, then the equation is written as, and it is very easy to transform the rectangular coordinates into polar coordinates. So from that calculus information, we write down this equation, and it can be written as 1 over r into d by dr of r rho ur plus 1 by r d by d theta of rho of u theta and d by dz of rho of uz. Remember, rho is there everywhere because of the compressibility possibility, and this is the equation that we will consider if we have to consider the cylindrical polar coordinates. The same equation then, and remember, we are considering steady motion, therefore no time derivative is occurring. In another circumstances, when the flow is not only steady, but it is also incompressible. If it is uncompressible, it means that the variation that can occur in the density of the fluid, for example, if the fluid is air or gases or anything of that type, then there will be no change in the density, and therefore the rho with respect to time will be 0 anyway because it's a steady, and at the same time the divergence, the effect of the divergence vector on rho will be 0, and therefore this equation, divergence of rho v, is then written as simply this. And in incompressible steady motion, the continuity equation, which is a very essential equation of fluid flow condition, generally we consider the conservation of mass, which is continuity equation, and the momentum equation, and the two together describes the fluid flow completely. For the moment, we are only discussing continuity equation, or which represent the law of conservation of mass. So incompressible continuity equation, we should write here actually that steady incompressible continuity equation in Cartesian coordinates in the component form can be written as this, where x, y, z are our rectangular coordinates and u, v, w are the components of velocity vector v in respective x, y, z directions. The same equation in cylindrical polar coordinates, it's so important that we write down this equation in polar coordinates also, because there are a lot of flows that occur in pipes that are circular, that are cylindrical in geometrical shape, and therefore it's very convenient to use the cylindrical coordinates so that the fluid flow is represented in an appropriate manner. This is the equation for cylindrical coordinates for steady and incompressible flow.